So, the parabola. Our formal definition, a parabola is the set of all points in the plane which are equidistant from a fixed point F called the focus and a fixed line L called the directrix. So let's get the right picture here. I'm going to select a line. I'm going to select this horizontal line, which we're going to call the directrix, D-I-R-E-C-T-R-I-X. We're going to pick a point. That's going to be our focus. And if this point over here, xy, is on the parabola, that's because the distance from the point to the focus is exactly equal to the distance from the point to the directrix. Now, in geometry, you would have learned that the way we describe, or the way that we find the distance from the point to the directrix, we look at perpendicular distance. So I need to take my directrix, form a perpendicular line. I want the perpendicular line that passes through this point. It absolutely must be perpendicular. This distance here and this distance here must be equal to each other, and that would get me a point on the parabola. Well, there's lots of points on the parabola that are going to satisfy that condition. This point out here, if I find the distance from the point to the focus, and then I find the perpendicular distance from the point to the directrix, if those two distances, this distance and that distance, are equal, then this point is also going to be on the parabola. Another easy point would be the point that is halfway between the focus and the directrix. That is going to be a special point. That is the vertex of the parabola. As you graph more and more and more of these points, you see the parabola shape start to come into being. You have your directrix, you have your focus, you have your vertex, which is perfectly halfway in between the directrix and the focus. The vertex is located at h, k. For this particular example, we see that the parabola is opening up. So in Algebra 2, we would say that a is greater than 0. From there, you'd be able to write your standard form of the parabola, y equals a, x minus h squared plus k. That would give you your directrix down here below the parabola. There's your vertex. The focus is inside the parabola. Now, a couple of things that we haven't discussed yet, but I'd like to, and I know we haven't done it this year in pre-calculus, but hang on, is how do you actually figure out the distance between the vertex and the directrix? Well, the distance is actually going to be 1 divided by 4 times a. So if a happens to be 2, then the distance between the vertex and the directrix would be 1 over 4 times 2, 1/8. I would start at my vertex and I would move down 1/8 of a space to get to the directrix. I would then move up 1/8 of a space to get to the focus. Additionally, I can use that a to figure out how wide the parabola is at the focus. This length is called the focal length. It is also known as the latest rectum, L-A-T-E-S-R-E-C-T-U-M. The length, the focal length, or the latest rectum, that is determined by taking the absolute value of 1 divided by a. So in my example earlier, when I said if a is 2, we'd move 1/8 of a space down from the vertex to get to the directrix. We'd move 1/8 of a space up to go from the vertex to the focus. The length of the parabola, or I guess the width at this point, would be 1/2. So from the focus, I would move 1/4 of a space to the right and 1/4 of a space to the left, and that's how I would get my perfect parabola that opens up. If I were to move the focus below the directrix, then I would actually reflect all of this over the directrix, and what you would wind up having is, if that's still the directrix, if that's the focus, you would have a parabola that opens downward. But all of the same properties apply. I could find the distance from the vertex to the focus by looking at 1 divided by 4a. I could find the focal length, or the latest rectum, absolute value of 1 over a, so I'd move half of that to the right, half of that to the left. Everything works the same way. Again, this year we haven't talked much about the latest rectum or the focus. Don't worry too much about that. Make sure that you're comfortable with the standard form. Make sure that you can find the vertex. Make sure you can determine the direction of opening. And then, of course, find the roots, x-intercepts, y-intercepts, all of that usual stuff applies. Let's look at the last type of parabola, and I think this was a relatively new one for us this year. This is going to be the parabola that opens sideways. So, parabola type 2. Same definition as before. What's different, if you see the graph, you see that this parabola is opening to the right. In Algebra 2, we always looked at parabolas that open up or parabolas that open down. Those are functions. This one clearly is not a function. It fails the vertical line test. The circle failed the vertical line test. The ellipse, the hyperbola, they all failed the vertical line test except parabola type 1. The way you would get a parabola opening to the right, you would pick a vertical directrix. You would then pick a point that is not on the directrix out here. We're going to call that the focus. You would then select points, just like we did before, that when I find the distance from the point to the focus, and then I find the distance from the point to the directrix, the distances are the same. I would grab all of the points in the xy plane that satisfy that definition. I'm going to form my parabola. If, good. The vertex is located over here at h comma k. If I needed to know the location of the directrix, the distance between the directrix and the vertex is still determined by 1 over 4a. The distance from the vertex to the focus is still determined by 1 over 4a. The focal length, right, that's going to be how wide is the parabola at the focus. That length of the orange segment is the absolute value of 1 over a. The parabola is going to open to the right. If a is a positive number, it's going to open to the left if a is a negative number. And the standard form for parabola type 2, it's an x equals a, parentheses, y minus k squared plus h. Want to be careful, your vertex is still located at h comma k, but the h and the k show up in different places. The h is actually what is outside the parentheses. The k is the opposite of what is inside the parentheses. And if a is greater than 0, it opens to the right. If a is less than 0, it opens to the left. So that's it for the big overview of standard forms, the definitions, generating the graphs. What we're going to do for the last couple of minutes is we're going to actually generate these different graphs for parabolas that have not been written in standard form. If you're in my pre-calculus class, this is where I want you to pause the video and I want you to practice the problems on your own. Generate the graphs for the next 4 or 5 conic sections. Once you're done, or if you want to do them one at a time, that's fine. Once you're done generating your graphs, hit play, continue watching the video, make the corrections to your problems if you made any errors. Good luck. So let's look at this. We have an equation. It has not been written in standard form, and depending on when you're watching this video in the context of the course, you might know right away from looking at this equation what you're looking at. What we focus on are the quadratic terms. I have 9x squared. I have negative 16y squared. Since these have opposite signs, if it's going to be any of the 4 conic sections, it's going to be the hyperbola. Now with the hyperbola, we have 2 kinds. We have the she's standing up or she's laying down. We're not going to worry right now about what type it is. It's too early in the game to make that declaration. What we're going to do for the next minute or two is we're going to get this into standard form. Well, in order to do that, we're going to grab the x's. So here's 9x squared minus 72x. plus we're going to grab the negative 16y squared minus 32y. We're going to move the 16 to the other side. In order to complete the square, the process that we use to find this magic number only works if you have a quadratic polynomial which has a leading coefficient of 1. It's the easy way to say that. You have an x squared. That's why we factored out the 9 to get this to be just x squared. Over here with the y, what we're going to factor out is a negative 16. When I do that, it leaves me y squared plus 2y. Now, in order to make this polynomial a perfect square trinomial, I need to figure out what's the magic number that to put there. If I have x squared minus 8x, what am I going to add over here? The way that we do that is you take the coefficient of the middle term, so negative 8, divide it by 2 and square it. The result is 16. I need for this constant term to be 16 in order for x squared minus 8x plus 16 to be a perfect square trinomial. I've added 16 inside the parentheses. I can't just do that. There is a cost, there's a transactional cost for doing that. If I add 16 in the parentheses on the left-hand side, I need to maintain my balance by adding something onto the right. You want to be careful. I've added 16 inside the parentheses, but that 16 ultimately is going to get multiplied by 9. 9 times 16 means I'm adding 144 to the other side. Let's look at the y's. I take 2 divided by 2 and I square that. I need to add 1 inside the parentheses. I added a 1 in the parentheses. That 1 is being multiplied by negative 16. I've added negative 16 on the left. I'm going to add a negative 16 on the right. I can now simplify this. I have 9. X squared minus 8x plus 16 is a perfect square trinomial. It's x minus 4 squared minus 16. The perfect square trinomial for y squared plus 2y plus 1 is y plus 1. All of that is equal to 16 and negative 16. That cancels out. That's 144. I'm close to having it in standard form. If it's going to be standard form of a hyperbola, I need this to be equal to 1. I need everything that's on the left equal to 1. The way we do that is we divide each of the terms by 144. I'm then going to reduce. On the right-hand side, 144 divided by 144 is 1. 16 and 144, there's a common factor of 16 here. So now we have y plus 1 squared over 9. Over here with the x's, the common factor for 9 and 144 is 9. So I have x minus 4 squared over 16, and I'm subtracting. We finally have it in standard form for a hyperbola. The center is going to be located at 4, negative 1. When I'm creating the box, the a is the square root of 16, so that's 4. That's how far left and right we're going to move. The b is the square root of 9, which is 3. That's how far up and down we're going to move. And if we want to find the foci are found by taking the square root of a squared plus b squared. So I'm going to take the square root of 16 plus 9. That's equal to 5. Well, let's put this all together with our hyperbola. I start at my center. I'm going to go 1, 2, 3, 4 to the right, down 1. 4, negative 1. A is 4, so I'm going to move 4 to the right. 1, 2, 3, 4. 8, negative 1. Move 4 to the left. 0, negative 1. We're going to move up 3. That puts me at 4, comma 2. I'm going to move down 3. 4, negative 4. I need the box. That is going to be used to determine the asymptotes. So I make the box. My next move is I create the diagonals for the box. Those are my asymptotes. Here are the asymptotes. I need to decide which way is the hyperbola opening. Since this is an x squared minus y squared hyperbola, she's standing up. So I start over here at 8, negative 1 and draw my hyperbola so it gets closer and closer and closer to the asymptote. And I also go down and I do that. I start at 0, negative 1. I move down and I move up. That's my hyperbola. For my pre-calculus students, that's as far as we've gone. If you want or need to locate the foci, that's where this value of c comes in. C was the square root of a squared plus b squared. That's equal to 5. The foci are always going to be inside the hyperbola. They're always on the transverse axis. So you'd start at the center. You'd move 5 spaces to the right. So that would put one focus at 9, -1. That would put the other focus at -1, -1. And that is an absolutely beautiful hyperbola. Some other questions you could be asked about the hyperbola. You might be asked to generate the equation for the asymptotes. And that might be initially a little worrisome, but it's actually pretty easy. Let's look at how we did this. The asymptotes both pass through the point 4, -1. So that is a point on the line for the asymptote. The other thing that I need to figure out is the slope of the line. Well, how did I generate the asymptote? I went 4 to the right. I went up 3 spaces. So the slope for this asymptote over here, the slope is 3/4. So I can use my point slope form of a line. Y equals 3/4 x minus 4 minus 1. That's the equation for that asymptote. I can have a similar conversation for my other asymptote. This asymptote also passes through the point 4, -1, but I form this line by going 3 spaces up and 4 spaces to the left. So the slope for this one is -3/4. The equation will be y equals -3/4 x minus 4 minus 1. What you're going to find always with the asymptotes is the slopes are going to have the same number value but opposite signs. That's it. That is a beautiful, complete hyperbola. I can't imagine you're needing to know much more than that. And you could probably take out the conversation we just had about finding the foci. We have 3 examples left. One of them is a parabola, one's a circle, one's an ellipse, and then we'll be done. All right, well, we've had a slight change in location since filming the first part of the video. We're going to go through these last couple of problems together. So this next conic section, 3x squared plus 4y squared plus 18x minus 32y minus 5 is equal to 0. I'm expecting it to be an ellipse. Again, I'm paying attention to the quadratic terms, the x squared and the y squared. I want to pay attention to the fact they're both positive. The numbers in front of them, the coefficients, are different. So if they're both positive and they're different, what we're expecting is an ellipse. So let's go through and do this. We grab the x terms together, 3x squared plus 18x, plus put the y terms together, 4y squared minus 32y. Let's move the 5 to the other side. Just like before, we're going to factor out the 3, leaving me x squared plus 6x. Over here, I factor out the 4, leaving me y squared minus 8y. The magic number, what I need to make this a perfect square, is going to be plus 9. Over here, I need a 16 for the same reason. -8 divided by 2 squared is 16. I now have 3. X squared plus 6x plus 9 is the perfect square, x plus 3 squared. Plus 4 times y squared minus 8y plus 16 is really y minus 4 squared, is equal to 5. I almost made a mistake there. We added a 9 over here that didn't exist before. That 9 is being multiplied by 3, so we have plus 27. We have a 16 that we've added inside the parentheses. That 16 gets multiplied by 4. That means we're adding 64. 64 plus 27 is 91, plus 5 is 96. If I'm going to get this in standard form, I'm going to go through and divide everything by 96, which gets me x plus 3 squared over 32, plus y minus 4 squared over 24 is equal to 1. The center for this ellipse is going to be located at -3,4. The a value is the square root of 32. What I need to know about the square root of 32 is I just need to be able to estimate it. I know that the square root of 25 is 5. The square root of 36 is 6. So the square root of 32 must be just a little bit less than 6. The b value is the square root of 24. That's going to be just a little bit less than 5. So let's go through and generate the graph. The center is at negative 3, 4. So 1, 2, 3 to the left, up 1, 2, 3, 4. That's my center. The a value is the square root of 32, so I'm going to go just a little less than 6 spaces to the right. So I'm going to go 1, 2, 3, 4, 5, not quite 6. That'll be negative 3 plus the square root of 32, comma 4. And then I'm going to go 1, 2, 3, 4, 5, not quite 6 spaces to the left. That's negative 3 minus the square root of 32, comma 4. Now let's figure out the b. The b is the square root of 24. So I'm going to go up 1, 2, 3, 4, not quite 5 to get to the point negative 3, 4 plus the square root of 24. I'm going to go down 1, 2, 3, 4, not quite 5 to get to negative 3, comma 4 minus the square root of 24. Because this is an ellipse, we're going to connect our 4 extreme points using an ellipse. Because the a value is the square root of 32, the length of the major axis is going to be horizontal in this case, is 2 times the square root of 32. The length of the minor axis is 2 times the square root of 24. Since the major axis is horizontal, we're going to call this the hamburger ellipse. For the most part of pre-calculus, that's as far as we've gone. If you needed to locate the foci, well, the foci are always on your major axis of symmetry. They're going to be somewhere over here, somewhere over here. The distance from the center to the foci is c. And remember, the way we find c is the square root of a squared minus b squared. So it's going to be the square root of 32 minus 24. C is the square root of 8, which is just less than 3. So I'm going to move square root of 3 spaces to the right. So just a little bit less than 3. 1, 2, not quite 3. I'll have negative 3 plus the square root of 8, comma 4. The other one, 1, 2, not quite 3 spaces to the left. Negative 3 minus the square root of 8, comma 4. And those are your 2 foci. That's everything you could ever be asked to find in, well, it's not everything you could ever be asked to find, but that's your ellipse. Other questions that you might be asked to find the x-intercepts for the graph. What am I asking? I want to know, where does your ellipse cross the x-axis? So if I was going to do that, we're not going to go through and do that exercise right now. I would set the y value equal to 0, and I'd solve it for x. And based on my graph, I'm expecting 2 x-intercepts. I could also ask you to find the y-intercepts. The y-intercepts, you're going to let x equal 0 and solve it for y. You can go through and ask all sorts of other questions, but when it comes to the ellipse, that's how you generate the complete graph, foci or no foci, and then you're set up nicely to answer all sorts of analytical questions like the domain and the range and all sorts of other good stuff. So let's move on. We have 2 conic sections still to go. All right, on to our third conic section. We have x squared plus 2 square roots of 2 times x plus y squared minus 7 equals 0. Looking at the quadratic terms, we have an x squared and a y squared. The leading coefficient for both of these is a 1, so they're equal to each other. They're both positive, so what I'm expecting is a circle. So let's do it. X squared plus 2 square roots of 2x plus y squared. I'm going to move the 7 to the other side. Already I can see things are good. The y squared, there's no y term. I don't have to worry about completing the square. It's already a perfect square. We already know part of the center. We're going to have to complete the square with the x's. Let's not worry. Let's not get too bogged down with the square root. The process is the same. You take the coefficient, divide it by 2, and you square it. If I do that, 2 square roots of 2 divided by 2, the 2's will cancel out. You get the square root of 2 squared, and the square root of 2 times the square root of 2 is 2. So I'm adding a 2 inside the parentheses over here. To balance it off, I add a 2 on the right. X squared plus 2 square roots of 2x plus 2, that is x plus the square root of 2 squared. Plus y squared is equal to 7 plus 2 is 9. So I have a circle. It's been written in standard form. The center is located at negative square root of 2 comma 0. The radius is equal to 3. The circle tends to be the easiest one to graph, so let's do this. Negative square root of 2. I go 1, not quite 2 to the left. My radius is 3, so I'm going to go 1, 2, 3 to the right. That puts me at negative square root of 2 plus 3 comma 0. I'm going to go up 1, 2, 3. That'll put me at negative square root of 2, 3. I'm going to go 1, 2, 3 to the left. That puts me at negative 3 minus the square root of 2 comma 0. And I'm going to go down 3. 1, 2, 3. That's going to put me at negative square root of 2, negative 3. All I need to do is connect those 4 points, make my circle. That's it. We're done. Again, we could have conversations about x-intercepts and y-intercepts. Well, because we have a circle centered on the x-axis and we've labeled our east and west points, we already have found our x-intercepts. If I want to find the y-intercepts, all I would have to do is I would let x equal 0 and solve it for y. Let x equal 0, solve it for y. For this one, I'm going to do it just because the question didn't ask me to, but let's go through the process. If I want to find the y-intercepts, we're going to go back to the original equation, and we're going to let x equal 0. So now, instead of x squared plus 2 square roots of 2x plus y squared minus 7 is equal to 0, we're going to let x equal 0. 0 squared plus 2 square roots of 2 times 0 plus y squared minus 7 is equal to 0. 0 plus 0. Y squared minus 7 is equal to 0. So y squared is equal to 7. Take the square root of both sides. Y is equal to plus or minus the square root of 7. I have a y-intercept up here at 0 square root of 7. And I have a y-intercept down here at 0 negative square root of 7. Done. Let's move on. All right, now we're on the last one. X equals negative 1/2 y squared plus 3y minus 9. This is already in x equals form. I have a y squared term, but I don't have an x squared term. So this would tell me right away that we're going to have a parabola. It's going to be a parabola either opening to the right or to the left. Because it's already in x equals form, I know this is the value of a. A is negative 1/2. It's going to be a parabola that opens to the left. We still need to complete the square, and with the parabola, the process for completing the square is a little bit different. It starts the same. We're going to factor out a negative 1/2. If I do that, what I'm left with is y squared minus 6y, and I'm going to leave the negative 9 over there. The original equation and this equation are identical. There's no difference. They're mathematically equivalent. What I want to do inside the parentheses is complete the square. So I take negative 6, I divide it by 2, and I square it. So I need to add positive 9 inside the parentheses. That 9 is being multiplied by negative 1/2. So what I've added on the right-hand side is a negative 9 over 2. Some students like to add the negative 9 over 2 to the other side. Let's look at that. So now I've got that expression. We added a 9 inside the parentheses when we completed the square. That 9 is multiplied by negative 1/2, so now we have negative 9 over 2. We added negative 9 over 2 on the right, so we added a negative 9 over 2 on the left to maintain our balance. But if we're going to get this into standard form, well, let's see. We've got negative 1/2. Y squared minus 6y plus 9 is the same thing as y minus 3 squared minus 9. It's not in standard form yet because of this negative 9 over 2, so I add 9 over 2 to both sides. The negative 9 over 2 and positive 9 over 2 cancel out. X equals negative 1/2 y minus 3 squared. A negative 9 plus 9 over 2, when you get a common denominator, you'll get negative 9 over 2. It's great. It's in standard form. The vertex for this one is located at negative 9 over 2, 3. Remember, standard form for an x equals parabola is x equals y minus k squared plus h. That's the h. That's the k. That's why my vertex is at negative 9 over 2, 3. The a is equal to negative 1/2, so I expect it's going to open that way. When I go to generate the graph, negative 9/2 is the same as negative 4.5. So 1, 2, 3, 4, and a little bit more. And then I'm going to go up 3 spaces, 1, 2, 3. That puts me at negative 4.5, 3 for the location of my vertex. And then I am opening to the left, so my parabola will look like that. There's my vertex. If you needed to find the directrix, if you needed to find the focus, if you needed to find the focal length, that's what I'm going to do now. If you don't need to do those, you can stop and feel good about the fact that you've generated the parabola and you've met all the expectations for the problem. But let's push ourselves a little bit here. Earlier in the video, we talked about the distance from the vertex to the directrix can be found by doing 1 over 4 times a. In our problem, a is 1/2. So this will be 1 over 4 times 1/2. 4 times 1/2 is 2, so 1/2. We're going to move 1/2 of a space to the right to reach the directrix. The directrix is a line. This is not an asymptote. I'm not drawing it as a dotted line. I moved 1/2 of a space to the right, so the directrix is located at the line x equals negative 4. That means that in order to get to the focus, I'm going to move 1/2 of the space in the other direction. That's going to put the focus at negative 5, 3. If I want to determine my focal length, the way that you find the focal length, how wide the parabola is, that is determined by the absolute value of 1 over a, which is 1 divided by 1/2. So we get 2. What that tells me is the focal length, starting at the focus, and if I go up to the parabola and down to the parabola, that length is 2. I'm going to cut that in half, so if the focus is at the point negative 5, 3, then this point is going to be at negative 5, 2. This point up here will be at negative 5, 4. The line segment that connects those two is your latest rectum. The midpoint of those two is your focus. You have your focus, you have your vertex, you have directrix. You have a complete problem. Feel free to high-five your neighbor or some loved one where you are. We are done. Congratulations.